The universe is not just expanding, it is accelerating into a void. This single fact is the greatest puzzle in all of science, a cosmic revelation that rewrites our story from beginning to end. By the time we finish, you will understand the 25 unsolved questions that define the very fate of reality. We will confront a force that makes up most of the cosmos yet is completely invisible, and grapple with whether time itself might be an illusion. Each mystery is a thread in a tapestry more wondrous and strange than any fiction. Are you ready to see how fragile our understanding truly is? At the heart of this cosmic upheaval is a single, profound question. What is dark energy? This is not just a mystery, it is a direct challenge to everything we thought we knew about how the universe works. For decades, the prevailing wisdom was simple. The universe began with the Big Bang, and ever since, the collective gravity of all the galaxies, stars, and matter has been pulling on the fabric of space, trying to slow the expansion down. It was a cosmic tug-of-war, and gravity was expected to win. Then, in the late 1990s, two separate teams of astronomers made a shocking discovery. By observing distant supernovae, the explosive deaths of stars, they found that the universe is not slowing down at all. It is speeding up. Something is actively pushing space itself apart, overwhelming the pull of gravity. That something was given a name, dark energy. It is a placeholder for our ignorance, a label for a force we cannot see, touch, or directly measure. Yet it appears to constitute roughly 68% of everything in the cosmos. To put that staggering number in perspective, all the stars, planets, gas, and dust you can see in every telescope image ever taken makes up less than 5% of the universe. Dark energy is the dominant component of reality, and we have no idea what it is. One leading idea goes back to Albert Einstein himself. He introduced a fudge factor into his equations of gravity, called the cosmological constant, to keep the universe static, which was the belief at the time. He later called it his greatest blunder when the expansion of the universe was discovered. Yet now, that same blunder might be the answer. Perhaps dark energy is an inherent property of empty space itself, a constant energy density that causes a repulsive gravity, pushing the universe apart. But if that is true, the calculated value is so bizarrely small and fine-tuned that it defies all theoretical explanation. It is like finding a single, specific grain of sand on a planet-sized beach and declaring it the most important object in existence. This is the central puzzle of modern physics, a phantom force writing the destiny of the cosmos on a blank page we cannot read. This brings us directly to the second great question. Is dark energy constant? Our entire projection for the fate of the cosmos rests on this single, terrifying variable. If dark energy is truly a fixed property of space, as Einstein's cosmological constant suggests, then the acceleration we see today will continue forever, growing steadily stronger. Galaxies beyond our own local group will eventually be pushed away so fast that their light can never reach us, leaving our sky an empty, lonely void. But what if dark energy is not constant? What if it is something that can change, grow, or even fade away? To answer this, cosmologists use a crucial number called the equation of state parameter, represented by the letter W. Think of it as the identity card for dark energy. A value of exactly -1 means it is the cosmological constant, unchanging and eternal. But if that number is different, even by a tiny fraction, everything changes. This search has led to fascinating alternative ideas like quintessence. Unlike a static constant, quintessence imagines dark energy as a dynamic field, almost like a fifth fundamental force of nature that permeates space. This field could evolve over time, its strength waxing or waning. In some models, it could grow so powerful it tears the very fabric of space apart in a cataclysm called the Big Rip. In others, it could decay and vanish, allowing gravity to reclaim control and possibly pull the universe back together in a big crunch. The difference between a forever expanding emptiness and a dramatic cosmic collapse hinges on this one number. Right now, the most precise measurements from telescopes and space observatories all point tantalizingly close to -1, but the uncertainty remains. We are like detectives trying to measure the thickness of a single sheet of paper from a mile away. The next generation of instruments, like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, are designed to measure this parameter with unprecedented precision. They will map billions of galaxies across cosmic time, looking for the subtlest shifts in the expansion rate. The goal is to see if W has always been the same, or if the push of dark energy has changed over the life of the universe. The answer will not just tell us what dark energy is, it will write the final chapter for everything that exists. This uncertainty about dark energy's nature makes the third question inevitable and profoundly personal. What is the ultimate fate of the universe? The answer is not just a scientific prediction. It is the final sentence in the story of everything, and it hinges entirely on the behavior of that mysterious force. Cosmologists have outlined 3 primary, breathtakingly dramatic possibilities for how it all might end. The first, and currently the most favored by our data, is the Big Freeze, also known as heat death. In this scenario, dark energy remains a constant, gentle push. The expansion continues forever, accelerating galaxies away from each other into an ever-darkening solitude. Over trillions upon trillions of years, stars will burn through their fuel and wink out. Black holes will slowly evaporate through a process called Hawking radiation. The universe becomes a vast, cold, and nearly empty void, where the temperature approaches absolute zero and no energy remains to create motion or life. It is a quiet, fading end, a cosmic sigh that stretches into eternity. The second possibility is far more violent. It is called the Big Rip. This fate awaits us if dark energy is not constant, but instead grows stronger over time. Imagine the repulsive force increasing so much that it overwhelms not just the gravity holding galaxy clusters together, but every force in nature. First, galaxy clusters would be torn apart. Then, individual galaxies. As the force intensifies, stars would be ripped from their orbits. Planets would be shredded. In the final moments, even atoms and atomic nuclei would be torn asunder, space itself ripping apart at a speed faster than light. The universe would end not with a whimper, but with a catastrophic, fundamental disintegration of reality. The third classic ending is the Big Crunch. This is the mirror image of the Big Bang, a cosmic reversal. For this to happen, the density of matter in the universe would need to be high enough, or dark energy would need to weaken and vanish, allowing gravity to finally win the tug of war. The expansion would slow, halt, and then reverse. Galaxies would begin rushing back toward each other. The universe would heat up as it collapses, eventually crushing all matter and energy back into an infinitely hot, dense point, potentially setting the stage for a new Big Bang and a cyclical universe. Current observations, measuring the flat geometry of the cosmos and the acceleration we see, strongly disfavor the Big Crunch. The data points toward the endless expansion of the Big Freeze. But that crucial word, points, holds everything. Our measurements are not yet precise enough to rule out a future where dark energy evolves. The difference between a frozen, eternal emptiness and a violent, sudden rupture depends on a decimal place in a number we are still struggling to pin down. We are forecasting the end of all things based on the faintest of clues, a shadow on the wall of a cave we have only just entered. Forecasting the end of all things forces us to look back to the very beginning, to a mystery that set the stage for everything we see. What caused the inflationary epoch? To understand the universe's fate, we must first understand its birth. The classic Big Bang theory, while powerful, left several cosmic puzzles unsolved. Why is the universe so remarkably smooth and uniform in all directions? Why is the geometry of space so flat? The answers seem to require a kind of cosmic magic trick in the first instance of existence. That magic trick is called cosmic inflation. The theory proposes that a fraction of a second after the Big Bang, the universe underwent a brief, unimaginably violent period of exponential expansion. Space itself stretched faster than the speed of light, doubling in size over and over again in a span of time so short it makes a blink seem like an eternity. This sudden growth spurt took a tiny subatomic patch of the early universe and blew it up to a size larger than our entire observable cosmos today. It smoothed out any wrinkles, flattened the geometry, and set the conditions for the more sedate expansion we see now. But this incredible idea begs the obvious question: what physical mechanism could possibly trigger and then abruptly stop such a colossal event? The leading suspect is a theoretical entity known as the inflaton field. Think of it as a cousin to the dark energy field, but operating under vastly different rules and at an energy scale we can scarcely comprehend. This field is thought to have permeated the newborn universe, trapped in a state of false vacuum, a kind of high-energy prison. While stuck in this state, it generated a powerful repulsive gravity, driving the explosive expansion of inflation. Then something happened. The field decayed like water freezing into ice, releasing its pent-up energy and transforming into the hot soup of particles that would become our universe. That decay, that transition, is what stopped inflation and lit the fuse for the standard Big Bang. Understanding the properties of this inflaton field is not just an academic exercise. It is the key to explaining why our universe looks the way it does. The quantum fluctuations in that field during its frantic expansion were stretched to cosmic scales, becoming the seeds for all the large-scale structure we see today. Every galaxy, every cluster, every vast cosmic web is a frozen imprint of those microscopic tremors from the first moment of time. We are, in a very real sense, the magnified echoes of quantum noise from the inflationary epoch. Yet the inflaton field remains purely theoretical. We have strong circumstantial evidence for inflation from the cosmic microwave background, the afterglow of the Big Bang, but we have no direct proof of the field itself or what laws governed it. Was it a unique event, or could it happen again in some distant corner of reality? The mechanism that started and stopped the birth of our universe is still a ghost in the machine, a fundamental question mark written into the foundation of everything. The echoes of that first explosive moment may not have been a singular event, but a single note in an infinite symphony. This leads us to the fifth, and perhaps most staggering question of all. Are there multiple universes? The idea of a multiverse is not science fiction, but a serious, albeit speculative, consequence of our leading theories about cosmic inflation. If the inflationary epoch was not a one-time event that started and stopped neatly, but instead a process that is eternal, then the implications are truly universe-shattering. In the model of eternal inflation, the rapid expansion of space does not end everywhere at once. Instead, it stops in localized patches, like bubbles forming in a vast, endlessly boiling cosmic pot. Each of these bubbles is a region where inflation has decayed, releasing its energy to create a hot Big Bang and a new universe with its own distinct properties. Our entire observable cosmos, with all its hundreds of billions of galaxies, would be just one such bubble in an incomprehensibly vast, ever-expanding multiverse. The fabric of space between these bubbles would still be undergoing runaway inflation, pushing them eternally apart, making them forever separate and unreachable. Within this infinite ensemble, the laws of physics themselves could be different in each bubble universe. In one, gravity might be 10 times stronger. In another, the nuclear forces that hold atoms together might be too weak for stars to form. The constants of nature, like the strength of dark energy or the mass of an electron, would not be fundamental, immutable truths, but more like local bylaws, set randomly when each bubble formed. This provides a potential and deeply controversial answer to one of the greatest puzzles in science, the fine-tuning problem. Our universe seems bizarrely perfect for life. If dark energy were slightly stronger, galaxies would never have formed. If the nuclear forces were slightly different, carbon, the essential element for life as we know it, would not be forged in stars. Why is our universe so hospitable? In a multiverse, the answer is a form of cosmic selection bias. In an infinite array of universes with every possible set of physical laws, we simply must find ourselves in one of the rare, habitable bubbles where conditions allowed for galaxies, stars, planets, and ultimately, observers to arise. We are not special, we are just lucky. The profound challenge, of course, is testability. By definition, other bubble universes are causally disconnected from our own. We cannot see them, communicate with them, or detect their influence. For many scientists, this places the multiverse on the border between profound physics and untestable philosophy. Yet, the idea persists because it emerges so naturally from our best mathematical descriptions of the universe's explosive birth. It is a ghost in the equations, a suggestion that our reality might be a single page in a book with an infinite number of chapters, each telling a completely different story of existence. The possibility of a multiverse forces us to re-examine the very foundations of our cosmic measurements. This brings us to a modern mystery so sharp and unresolved, it has split the cosmology community, known as the Hubble tension. At its core is a deceptively simple number, the Hubble constant. This is the current expansion rate of the universe, telling us how fast galaxies are receding from us for every megaparsec of distance. A megaparsec being about 3.26 million light years. For decades, the holy grail of cosmology has been to pin down this number with perfect precision. Instead, we have found two different answers, and they refuse to agree. The first method looks back to the infant universe, to the cosmic microwave background. This ancient light, a snapshot from when the universe was only 380,000 years old, is exquisitely detailed. By studying its subtle patterns, scientists can calculate what the expansion rate should be today, assuming our standard model of cosmology, called lambda cold dark matter, is correct. This method is like reading the blueprint of the universe's birth and then running the simulation forward to predict the present. The second method works in our cosmic neighborhood. Astronomers use so-called standard candles, objects like certain supernovae and pulsating stars called Cepheid variables, whose intrinsic brightness we know. By measuring how bright they appear from Earth, We can calculate their distance incredibly accurately. Then, by measuring how much their light has been stretched or redshifted by the expansion of space, we get a direct local measurement of the Hubble constant. This is like placing mile markers along a highway and using a radar gun to measure the speed of cars right in front of us. Both methods are monumentally precise, the result of Nobel Prize-winning work. And that is what makes the results so deeply troubling. They disagree. The early universe measurement from the cosmic microwave background gives a slower expansion rate, around 67 kilometers per second per megaparsec. The local measurement from supernova and stars gives a faster rate, around 73. The gap might seem small, but the precision of each measurement is so high that the chance this is a simple error is vanishingly small, less than 1 in a million. This is the Hubble tension. It is not a minor discrepancy, it is a 5 sigma problem, a glaring crack in the foundation of our cosmic model. It suggests one of two earth-shattering possibilities. Either there is a systematic error in one of our measurements that has eluded the world's best minds for over a decade, or our standard model of cosmology is incomplete. Perhaps dark energy is not constant, but evolving in a way we have not accounted for. Maybe there is a new type of neutrino, or some other exotic particle from the early universe subtly altering the expansion history. Some have even speculated about a feature in the primordial power spectrum from inflation, a wrinkle in the very first moments that changes the calibration. The tension is a beacon pointing toward unknown physics. It is a reminder that the universe is under no obligation to make sense to us, and that our most cherished models are only maps, not the territory itself. Solving this puzzle may require not just better data, but a fundamental rethinking of the cosmic story we thought we knew. That crack in our cosmic model forces us to ask a question that is both deeply scientific and profoundly philosophical. Is the universe finite or infinite? This is not a question about what lies beyond the observable universe, but about the fundamental shape and size of reality itself. To answer it, cosmologists do not build a ruler big enough to measure the cosmos. Instead, they measure its geometry, its curvature. Think of it like this. An ant on the surface of a perfectly flat sheet of paper can draw a triangle, and the angles will always add up to exactly 180 degrees. That is Euclidean geometry. But if that ant is on the surface of a sphere, a closed geometry, the angles of a large triangle will add up to more than 180 degrees. On a saddle-shaped surface, an open geometry, they will add up to less. We perform the same experiment on a cosmic scale. We look at the largest possible triangles we can find, using patterns in the cosmic microwave background as their sides. The result from mission after mission is remarkably precise. The angles add up to exactly 180 degrees. The universe, as far as we can measure, appears to be geometrically flat. This finding has a staggering implication. In the standard model of cosmology, a flat universe is most simply explained by it being infinite in extent. It has no edge, no boundary. It just goes on forever with galaxies, stars, and possibly even copies of you and me, stretching out without end. The idea is dizzying. It means that every possible history that could have unfolded within the constraints of physics has unfolded somewhere in that infinite expanse. It means our entire observable universe, with its hundreds of billions of galaxies, is just an infinitesimal speck in an unbounded whole. But a flat geometry does not absolutely demand infinity. It could also be consistent with a finite universe that is shaped like a torus. Like a video game screen, where if you go off one edge, you reappear on the other. This would be a universe without a boundary, but with a finite volume. The challenge is we cannot see any repeating patterns, any ghostly images of the same galaxy cluster in different directions, which we would expect if the cosmos wrapped around on itself. So the data strongly leans toward the infinite interpretation. The philosophical weight of this is immense. A finite universe feels containable, knowable in principle. An infinite universe is fundamentally unknowable. We could never catalog all of it, not even in an infinite amount of time, because new regions forever move beyond our cosmic horizon due to the expansion of space. It places a permanent limit on human knowledge. We are confined to our observable bubble, a finite island in what may be an endless sea, and that horizon is always shrinking in terms of what we can one day reach, as dark energy pushes the most distant galaxies away faster than light can bridge the gap. So we are left with a profound irony. Our most precise measurements tell us the universe is flat, hinting at infinity, yet we are forever trapped within a finite and ever-shrinking sphere of influence. We may be citizens of an infinite cosmos, destined to only ever know our own lonely, fading neighborhood. Our confinement to a finite observable bubble is shaped by a force we cannot see, the cosmic scaffolding of dark matter. This brings us to the eighth great question, one that is deeply intertwined with the story of expansion. What is the nature of dark matter? We have spoken of dark energy as the dominant force pushing the universe apart, but dark matter is its silent, anchoring counterpart. Composing roughly 27% of the cosmos, it is the invisible skeleton upon which the visible universe is built. Its gravitational pull is what first gathered clouds of primordial gas, allowing galaxies and galaxy clusters to form. Without dark matter, the gravitational tug-of-war in the early universe would have been too weak, and stars might never have ignited. But for all its profound influence, we have never directly detected a single particle of it. We know it exists because we can see its gravitational handiwork. We watch stars orbit the centers of their galaxies far too quickly, held in place by the grip of unseen mass. We observe how massive galaxy clusters bend the light from objects behind them, an effect called gravitational lensing, and the amount of bending tells us there is far more matter there than the glowing stars and gas account for. Dark matter is the ghost in the cosmic machine, and its identity is one of physics' greatest hunts. The leading candidate for decades has been a theorized particle called a WIMP, which stands for Weakly Interacting Massive Particle. As the name suggests, these particles would interact only through gravity and the weak nuclear force, making them incredibly difficult to catch. They would be heavy, slow-moving, and flood the universe, forming the vast, diffuse halos that engulf galaxies. Yet despite monumental efforts, with detectors buried deep underground to shield from cosmic noise, no definitive WIMP signal has been found. This has led scientists to seriously consider other possibilities, like the action. An action is a hypothetical particle born out of a solution to a different problem in particle physics. It would be extraordinarily light, billions of times lighter than an electron, and behave more like a wave than a discrete particle. If actions are the answer, they could form a strange, coherent cloud permeating the galaxy. The properties of dark matter are not just a particle physics puzzle. They are critical to cosmology's big picture. How dark matter clumps and moves under gravity dictates the growth of the cosmic web, the vast filamentary structure of galaxies we see today. Different types of dark matter, like cold, slow-moving particles versus warm, faster ones, would weave that web differently, changing the timing and distribution of the first galaxies. This matters immensely for understanding expansion. When we use distant supernova or galaxy clusters to measure how the universe has grown over time, we must first understand how the gravitational scaffolding of dark matter has evolved. If we are wrong about dark matter's basic nature, we could be misinterpreting the expansion history itself. The hunt is more than a search for a missing particle. It is an attempt to read the hidden blueprint of the cosmos, a blueprint written in a substance that refuses to speak to us except through the silent language of gravity. The silent blueprint of dark matter was supposed to guide a slow, stately construction of the cosmos. But new eyes on the sky are revealing a universe that built its greatest structures in a frantic, almost impossible rush. This is the ninth great question. How did galaxies form so quickly? The timeline written in our standard models is clear. After the Big Bang and inflation, the universe was a hot, smooth soup of particles. It took hundreds of millions of years for gravity to slowly tug on the subtle ripples imprinted by inflation, gathering dark matter into halos, which then pulled in gas to eventually ignite the first stars and birth the first, small, primitive galaxies. These were the cosmic dark ages, a long, quiet dawn. But the James Webb Space Telescope, with its unprecedented power to peer back to the universe's infancy, is showing us a picture that does not match that patient story. Webb is seeing galaxies that are not just present in the very early universe, they are shockingly mature. It has spotted galaxies with hundreds of billions of stars, galaxies with complex shapes and central bulges, and supermassive black holes at their hearts, all existing when the universe was only 3 or 4% of its current age. According to our old scripts, these behemoths should not have had the time to assemble. It is like walking into a nursery and finding a room full of fully grown adults. This creates a profound timing puzzle. Either the seeds for these galaxies were planted much earlier than we thought, or the process of galaxy formation was radically more efficient and rapid in the early cosmos. One possibility is that the very first stars, known as population 3 stars, were monstrously huge and short-lived, exploding violently and seeding space with heavy elements at a breakneck pace. This could have jump-started the next generation of star formation in a furious chain reaction. Another, more disruptive idea is that our understanding of the early expansion conditions is off. Perhaps the density of matter in certain regions was higher, or the nature of dark matter itself allowed for faster clumping. Some scientists are even revisiting the possibility that small, direct collapse black holes from the primordial universe acted as instant gravitational anchors, around which galaxies could form with astonishing speed. Each of these potential solutions forces us to re-examine the delicate interplay between the expansion of space, driven by dark energy, and the contraction of matter, guided by dark matter. If galaxies formed faster, it means the gravitational tug-of-war in the early universe had a different balance. The James Webb data is not just showing us ancient objects, it is handing us a stopwatch that seems to be ticking at the wrong speed for our cosmic models. The infancy of the universe appears to have been a period of explosive, precocious growth, and we are only beginning to understand the rules of that strange and distant nursery. The frantic pace of the early universe is written in light, in a faint afterglow that holds our deepest cosmic secrets. This brings us to the 10th great question: what is the dipole anisotropy? To find it, we must look at the oldest picture we have, the cosmic microwave background. This radiation is the cooled remnant of the Big Bang's fireball, a nearly perfect blanket of microwaves bathing the entire sky. For decades, it has been the gold standard for our cosmology, its incredible uniformity confirming that on the largest scales, the universe looks the same in every direction, a tenet known as the cosmological principle. But when scientists made exquisitely precise maps of this background, they noticed something odd. One half of the sky is ever so slightly warmer than the other half. This temperature difference is minuscule, a variation of only about 1 part in 1,000, but it is undeniably there. It forms a pattern called a dipole, with a hot pole and a cold pole. The standard explanation is straightforward and comforting. It is thought to be a Doppler effect caused by our own motion. Just as an ambulance siren sounds higher pitched as it moves toward you and lower as it moves away, the microwave background appears warmer in the direction we are heading and cooler in the direction we are leaving. This measured motion is our solar system's journey around the Milky Way, combined with the galaxy's own drift through space. It is a local effect, a simple result of our own seat on a moving cosmic train. But what if it is not that simple? Recent, more precise measurements have begun to reveal a disturbing wrinkle. The dipole we see in the cosmic microwave background seems to align suspiciously well with other, much larger dipoles. Astronomers see a similar pattern in the distribution of distant quasars and galaxies across the sky. These objects, billions of light years away, also show an apparent asymmetry that points in roughly the same direction as the one in the ancient microwave light. This coincidence is deeply unsettling. It suggests the possibility that the dipole is not just a reflection of our local motion. It might be evidence of something far grander and more troubling, a large-scale bulk flow of galaxies, as if entire superclusters are being pulled like leaves in a cosmic river towards some immense, unseen gravitational attractor beyond our horizon. An even more radical interpretation challenges the very heart of modern cosmology. Could this dipole be an intrinsic feature of the universe itself? Could it mean that the expansion of space is not perfectly uniform, that on the largest scales, one direction of the cosmos is stretching slightly faster than another? This idea directly contradicts the cosmological principle, the foundational assumption that the universe is homogeneous and isotropic, the same everywhere and in every direction. If that principle fails, our entire cosmic model, from the Big Bang to dark energy, is built on shaky ground. We would have to accept that we do not live in a typical region of space, that our universe has a preferred direction, a cosmic tilt that redefines our place in the whole. The dipole anisotropy is a tiny signal with monumental implications. It is a whisper from the edge of the observable universe, hinting that our smooth, uniform cosmos might have a grain, a texture, a fundamental lopsidedness we are only just beginning to perceive. That faint, uniform afterglow from the Big Bang is more than a simple picture. It is a cosmic ledger. The first few minutes of the universe were a frantic forge, a nuclear reactor of unimaginable scale where the very first atomic nuclei were created. This process, called Big Bang nucleosynthesis, produced the primordial ingredients for everything to come, and it left a specific fingerprint in the amounts of light elements we see today. The calculations are breathtakingly precise, based on the known density of ordinary matter and the expansion rate of the universe during those first critical minutes. Physicists can predict exactly how much hydrogen, helium, and lithium should have been cooked up. For hydrogen and helium, the predictions match the observed abundances in the oldest stars and gas clouds almost perfectly. It is a stunning confirmation of our model for the universe's first 3 minutes. But there is one glaring exception, a single entry in the ledger that does not add up. This is the lithium problem. According to the theory, the early universe should have produced about 3 times more lithium-7. the most common isotope of lithium, than what we actually measure in the atmospheres of ancient stars. We are missing 2/3 of the universe's primordial lithium. It is a small number with potentially huge implications. Where did it go, or was it never made in the expected amounts to begin with? One possibility is that our understanding of stellar physics is incomplete. Perhaps these ancient stars have internal processes that slowly destroy lithium over billions of years, hiding the true primordial abundance. But the evidence is mixed, and many astronomers suspect the problem goes deeper, back to the physics of the Big Bang itself. The predicted amount of lithium is exquisitely sensitive to conditions in that first nuclear forge, particularly the density of protons and neutrons, and how fast the universe was expanding during those initial minutes. If the predicted lithium is wrong, it could be a sign that something was different in that primordial environment. Could there have been an unknown particle, something that decayed or interacted in a way that altered the nuclear reaction rates? Some theories propose a form of exotic dark matter that was present and active in those first moments, subtly changing the balance of particles. Others suggest a temporary change in the fundamental forces themselves during that hyper-dense phase. Each of these ideas would not just solve the lithium puzzle, it would rewrite the conditions of the early universe's expansion. The rate at which space was stretching during nucleosynthesis is a critical parameter locked into those elemental abundances. If we have to adjust our model to account for the missing lithium, we might also be adjusting the expansion history of the cosmos in its infancy. This tiny discrepancy, this one wrong number in a sea of correct predictions, is a ghost from the first 3 minutes. It whispers that our picture of the universe's violent birth, while overwhelmingly successful, might still be missing a crucial piece of physics, a shadow player that altered the recipe at the very dawn of time. That ghost from the first 3 minutes haunts a much larger, more fundamental mystery. Why is the universe so smooth? Look up at the night sky, and in every direction you see a cosmos of staggering complexity with galaxies and voids. But when we zoom out to the largest possible scales, a profound simplicity emerges. The universe is remarkably, almost eerily, uniform. The most dramatic proof of this is the cosmic microwave background, that ancient afterglow. No matter which patch of sky we point our telescopes toward, its temperature is the same to an astonishing degree of precision, about 2.7 degrees above absolute zero. The variations are only about 1 part in 100,000, mere whispers against a constant hum. This smoothness presents a deep logical puzzle known as the horizon problem. To understand it, think about a simple fact of cause and effect. Nothing, not even light or heat, can travel faster than light. This sets a limit on how far apart 2 points in the universe could have been in contact with each other since the Big Bang. Now, consider 2 points on opposite sides of the observable sky. Their light is only now reaching us, but they are separated by nearly 90 billion light years. According to the standard Big Bang timeline without inflation, these 2 regions were never close enough for light or heat to travel between them. They were outside each other's cosmic horizons, forever causally disconnected. Yet they have the exact same temperature. How did they coordinate this? It is as if 2 chefs in kitchens on opposite sides of the planet, who have never spoken or shared a recipe, somehow pulled identical cakes out of their ovens at the same moment. Without some form of connection, this perfect thermal equilibrium is impossible. This is the horizon problem, a glaring flaw in the classic Big Bang story. The leading solution, as we have touched on, is cosmic inflation. The theory proposes that in the first fraction of a second, a tiny subatomic patch of space, which was in perfect thermal contact with itself, underwent that violent exponential expansion. This microscopic region, already uniform and in equilibrium, was stretched to a size larger than our entire observable universe today. What were once neighboring points, close enough to share temperature, were blown apart to become opposite ends of the cosmos. Inflation takes a small, smooth region and magnifies it to cosmic proportions, explaining the large-scale uniformity we see. It elegantly solves the horizon problem by giving the entire observable universe a common origin point, a shared history of contact before the great stretching began. But while inflation is a beautiful and powerful idea, we must ask a critical question. What direct evidence do we have for this mechanism beyond its neat explanatory power? The strongest clues come, again, from the cosmic microwave background. Inflation predicts that the quantum fluctuations in the inflatoned field would have been stretched to cosmic scales, creating minute density variations. These variations should have specific statistical properties, a particular fingerprint, the patterns we see in the microwave background, the specific way the hot and cold spots are distributed, match this inflationary fingerprint with incredible precision. It is like finding a suspect's unique shoeprint at the scene of a crime. Furthermore, inflation naturally predicts a flat universe, which our geometry measurements confirm. So the evidence is compelling, but it is largely circumstantial. We see the outcome the theory predicts, but we have never observed the inflattened field itself or the process in action. Some scientists argue that while inflation solves the problems, it does so at a cost, becoming so flexible that it can explain almost any outcome, making it difficult to falsify. The search for more direct proof continues, with cosmologists looking for faint imprints in the polarization of the microwave background, or for traces of primordial gravitational waves, ripples in spacetime from the inflationary burst itself. For now, the incredible smoothness of our cosmos stands as a silent monument to its violent, frenzied birth, a uniformity so perfect it demands a story of exponential magic, a story we are still learning how to read. That smooth, uniform cosmic background is not as featureless as it first appears. Buried within its subtle temperature variations is a pattern so strange and unsettling that cosmologists have given it a name worthy of a cosmic thriller, the axis of evil. This is not a malevolent force, but a statistical anomaly that sends a chill down the spine of our standard models. The problem begins with a simple, beautiful assumption, the cosmological principle. This principle states that on the largest scales, the universe has no special place and no special direction. It should look the same everywhere and in every way. The cosmic microwave background is our best test of this idea, and while it is incredibly uniform, its tiny fluctuations, the hot and cold spots, should be randomly scattered across the sky like a cosmic fingerprint with no rhyme or reason. But when scientists began to analyze the patterns in these fluctuations, they noticed something that defied all statistical expectation. Certain large-scale features, alignments of hot and cold spots stretching across billions of light years, seem to be curiously coordinated with our own local cosmic backyard. Specifically, these features appear to align with the plane of our solar system, the ecliptic, and the direction of the sun's motion through the galaxy. This is an alignment that should be utterly impossible in a truly random, isotropic universe. It is as if you painted a masterpiece by randomly splattering paint on a canvas, but then discovered the largest splatters formed a perfect arrow pointing directly at your own eye. The probability of this happening by pure chance is astronomically low, less than 1 in 10,000. So what could explain the axis of evil? The first and most hopeful possibility is that it is a systematic error, a ghost in our own machines. Perhaps some unknown contamination from our solar system, or an unforeseen quirk in the data processing of satellites like Planck and WMAP, is imprinting this false signal onto the cosmic map. Scientists have hunted for this kind of error for years, but the stubborn signal persists. If it is not an error, the implications are revolutionary. It could mean the universe has a preferred direction, a cosmic grain, like wood that is easier to split along one axis than another. This would shatter the cosmological principle, the very bedrock of modern cosmology. Our entire framework for understanding the Big Bang, dark energy, and the universe's evolution is built on the assumption of isotropy. If the universe has a fundamental lopsidedness, an axis along which structures align or expansion varies, we would have to rewrite the textbooks from the first page. Some theorists have proposed wild but fascinating ideas to explain it. Could it be a remnant imprint from before the Big Bang, a scar from a collision with another universe in a multiverse landscape? Or is it evidence that the fabric of spacetime itself is subtly anisotropic, stretching differently in one direction than another, which would mean the force of dark energy is not uniform? The axis of evil remains an open wound in our cosmic maps. It is a whisper that our place in the universe might not be so average after all, that the cosmos might have a spine, and we are aligned with it. Whether it is a profound clue or a persistent mirage, this anomaly reminds us that the universe is under no obligation to conform to our elegant assumptions. That unsettling possibility of a lopsided cosmos forces us to question something even more fundamental: the stability of reality's rulebook. Are the fundamental constants changing? We have always assumed that the laws of physics are immutable, the same yesterday, today, and forever. The speed of light, the strength of gravity, the charge of an electron, these are the fixed numbers upon which we have built our entire understanding of the universe, from the quantum world to the cosmic scale. But what if they are not fixed at all? What if the very rules of the game have been slowly shifting over the vast expanse of cosmic time? This is not science fiction, but a serious line of inquiry driven by some of the most precise astronomical observations ever made. The prime suspect in this investigation is a number known as the fine structure constant, often represented by the Greek letter alpha. This constant is a pure number, a combination of the charge of the electron, the speed of light, and Planck's constant. It governs the strength of the electromagnetic force, which is responsible for holding atoms together, for the chemical bonds that create molecules, and for the light that stars emit. In essence, alpha dictates how strongly light and matter interact. If its value were even slightly different, the universe would be unrecognizable. Make it a bit larger, and atomic nuclei could not hold together. Make it smaller, and complex molecules necessary for life might never form. For decades, physicists have assumed alpha is a true constant, but a team of astronomers, using the light from incredibly distant quasars as a cosmic time machine, has reported a startling finding. By analyzing the absorption lines in this ancient light, lines created by clouds of gas billions of light years away, they claim to see a subtle shift. Their data suggests that billions of years ago, in the early universe, the value of the fine structure constant was minutely smaller than it is today. The change is tiny, a few parts in a million, but if true, the implications are earth-shattering. A varying constant would mean that the electromagnetic force was slightly weaker in the past. This would directly affect how atoms absorbed and emitted light long ago, which is exactly what these astronomers believe they are seeing imprinted in the quasar spectra. The scientific community remains deeply divided. Other teams, using different telescopes and methods, have failed to confirm the result, finding no evidence of change. The measurements are at the very edge of our technological capability, a whisper at the limits of noise. Yet the possibility alone is a seismic shock to our models. If alpha has changed, it forces a cascade of revisions. Stellar evolution would be rewritten because the nuclear reactions that power stars depend critically on the strength of electromagnetism. The age estimates of the oldest stars, based on our current constants, could be wrong. Even the expansion history of the universe would need re-examination, because the behavior of matter and radiation in the early cosmos, which sets the initial conditions for expansion, is tied to these fundamental numbers. A drifting constant could be a sign of something profound, like extraspatial dimensions predicted by string theory slowly unfurling over cosmic time, or a dynamic field, similar to the inflaton or quintessence, that subtly alters the fabric of physics as it evolves. It raises a haunting question. Are we seeing the universe through a lens of permanent, stable laws? Or are we merely catching a single frame in a slow-motion film where the rules themselves are part of the story? The search for an answer is a race to measure the faintest of ghosts, a quest to determine if the bedrock of reality is stone or shifting sand. The possibility of drifting constants hints that the universe itself might be a dynamic, evolving entity, its rules written in fading ink. But there are other messengers from the depths of space, not made of light, that carry tales of even more violent and extreme events. They are cosmic rays, subatomic particles screaming across the cosmos at nearly the speed of light. Most are protons or atomic nuclei with relatively modest energies, but a tiny fraction belong to an elite, mysterious class. These are the ultra-high-energy cosmic rays, and they present us with a monumental puzzle. Their energies are staggering, millions of times greater than anything we can produce in the most powerful particle colliders on Earth. A single one of these subatomic bullets carries the kinetic energy of a professionally thrown baseball, all packed into a particle smaller than an atom. The sheer existence of such particles is a profound mystery. What cosmic engine in the universe could possibly accelerate a single proton or nucleus to such an insane velocity? It requires conditions of almost unimaginable violence. Theorists point to the most extreme objects we know, the furious jets blasting from the cores of active supermassive black holes, where matter is torn apart and magnetically hurled across space. The colossal shock waves from merging galaxy clusters, where magnetic fields can act as particle slingshots on a cosmic scale. Or perhaps the cataclysmic deaths of the most massive stars, in hypernova or the birth cries of magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's. Yet, identifying the exact source is incredibly difficult. These particles are electrically charged, which means they do not travel in straight lines. As they streak across the universe, they are bent and deflected by the weak but pervasive magnetic fields that thread the space between galaxies. By the time one finally strikes Earth's atmosphere, creating a cascade of secondary particles we can detect, it is impossible to simply look back along its path and see where it came from. It is like trying to find the origin of a leaf blown into your yard after a hurricane. Its journey has been twisted and turned beyond recognition. This brings us to the second part of the mystery, a journey directly tied to the expansion of the universe itself. These particles are not just incredibly energetic, They have traveled across billions of light years of expanding space. And space is not empty. It is filled with the cosmic microwave background radiation, that faint afterglow of the Big Bang. For an ultra-high-energy proton traveling at such a fantastic speed, this sea of photons is not a gentle background hum. It is a thick fog. When the high-energy proton collides with one of these microwave photons, it loses energy, producing other particles. Over a very long distance, this effect, called the Greisen-Zatsepin-Kuzmin or Giesecke limit, should act as a cosmic speed limit, robbing the most energetic particles of their energy before they can reach us from too far away. This creates a cosmic horizon. We should not see ultra-high-energy cosmic rays from sources more than about 150 million light-years away. But here is the twist. When astronomers look within that relatively local volume of space, they do not see any obvious, sufficiently violent cosmic power plants aligned with the arrival directions of these rays. The sources appear to be blank spots in the sky. This means one of two equally fascinating things. Either our understanding of how particles lose energy in an expanding universe filled with radiation is incomplete, or these rays are coming from something entirely new and hidden within our local cosmic neighborhood, a source so powerful and exotic we have not yet learned to see it. Each of these rare, ultra-high-energy events is a postcard from a cosmic catastrophe, its message scrambled by magnetic fields and the relentless expansion of space. Decoding it would not just reveal a new class of astronomical object. It would provide a radical test of how matter and energy propagate through the evolving fabric of the cosmos itself. The journey of those high-energy cosmic rays ends in our atmosphere, but their story began in a universe that was once completely dark. This darkness was not an absence of light, but a cosmic fog so thick it trapped the first rays of starlight for millions of years. We call this transformative era the epoch of reionization, and it is one of the most important yet least understood chapters in the history of the cosmos. To understand it, we must travel back to a time when the universe was a very different place. After the Big Bang cooled and the first atoms formed, the cosmos entered the cosmic dark ages. Space was filled with a neutral gas, primarily hydrogen, that absorbed ultraviolet light like a dense, pervasive mist. For hundreds of millions of years, the universe was truly dark, with no stars or galaxies to pierce the gloom. Then something changed. The first structures ignited. The very first stars, known as population 3 stars, are thought to have been monsters, hundreds of times more massive than our sun. They burned hot, bright, and fast, flooding their surroundings with intense ultraviolet radiation. This fierce light did something extraordinary. It began to strip the electrons from the neutral hydrogen atoms, turning them into free protons and electrons in a process called ionization. Think of it as a cosmic sunrise slowly burning off a morning fog. One by one, then in growing numbers, these brilliant stars and the first small galaxies punched ionized bubbles into the neutral hydrogen fog. These bubbles grew and overlapped, eventually clearing the fog entirely and making the universe transparent to light, the state it remains in today. This is the epoch of reionization, the moment the cosmic lights turned on for good. But the details of this grand transition are shrouded in mystery. We do not know exactly what did the work. Were the primary drivers those first, monstrously massive stars? Or were they the supermassive black holes at the centers of the earliest galaxies, whose ferocious energy output as they consumed matter could have been even more effective at ionizing the gas? Or was it a combination, with different sources dominating at different times? The timeline is also hotly debated. Did reionization happen quickly, a sudden flash that cleared the fog in a cosmic instant? Or was it a slow, gradual process that sputtered along for hundreds of millions of years? The answers are written in the light from the most distant objects we can see, but reading that light is incredibly difficult. The neutral hydrogen fog itself is what we are trying to see through, so observing it directly is a profound challenge. Astronomers use ingenious tricks, like looking for the specific absorption signature that neutral hydrogen imprints on the light of even more distant quasars, acting as cosmic lighthouses shining through the fading mist. New telescopes, like the James Webb, are now peering directly into this era, hunting for those first, faint galaxies to see if they are numerous and bright enough to have done the job. Why does this ancient fog matter for our story of expansion? Because the epoch of reionization is a critical link in the chain of cosmic structure formation. It marks the moment when light finally escaped, when radiation began to exert significant pressure on the gas, influencing how and where the next generations of galaxies could form. The timing and nature of reionization are directly tied to the expansion rate of the universe at that time. A faster expansion would have spread matter out more thinly, potentially delaying the formation of the first ionizing sources. A slower expansion would have allowed structures to clump together more quickly. By piecing together the story of reionization, we are essentially taking the universe's temperature during its adolescence, checking if the growth spurt predicted by our models of dark matter and dark energy matches the evidence written in that ancient, clearing fog. It is a crucial cross-check on our entire cosmic timeline, a test to see if the shadowy scaffolding of the early universe aligns with the brilliant, transparent cosmos we inhabit today. That ancient, transparent cosmos we inhabit today is built from a substance that should not exist. Why is there more matter than antimatter? This is not a minor puzzle. It is the ultimate question of our own existence. The laws of physics, as we understand them, are almost perfectly symmetrical between matter and its mirror opposite antimatter. For every particle like an electron, there is an antiparticle, a positron, with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy. According to our best theories of the Big Bang, the universe should have created these two forms in absolutely equal amounts. In the searing heat of the first moments, particle-antiparticle pairs would have popped into existence from the energy of the expanding universe, only to immediately collide and vanish back into radiation. If that perfect symmetry had held, every last bit of matter would have found its antimatter counterpart. The entire universe would have annihilated itself, leaving behind nothing but a fading sea of light, a cosmos devoid of stars, planets, or life. Yet here we are. Everything you see, from the screen in front of you to the most distant galaxy, is made of matter. Somehow, in the earliest instance of the universe's frantic expansion, a tiny, almost imperceptible imbalance was introduced. For every 1 billion particles of antimatter created, there were 1,000,000,001 particles of matter. That 1 in a billion excess is all that survived the Great Annihilation. It is the residue from which every atom in your body was forged. This staggering fact is known as the Baryon asymmetry problem, and solving it requires physics to break its own most cherished rules. In the 1960s, physicist Andrei Sakharov outlined the 3 conditions needed for a matter-dominated universe to emerge from a symmetric beginning. First, there must be processes that violate the conservation of Baryon number, meaning the total amount of matter can change. Second, the symmetries of charge and parity must be violated, meaning the universe must treat matter and antimatter slightly differently, not as perfect mirrors. And third, these processes must occur out of thermal equilibrium, during a period when the universe was expanding and cooling so rapidly that the system could not smoothly readjust back to perfect symmetry. Think of it like a pot of water supercooled below freezing. Give it a jolt, and it will crystallize into ice in an instant, locking in a new state. The early, hyper-expanding universe provided that jolt. The search is for the specific mechanism, the particle or interaction, that could fulfill all three Sakharov conditions during that brief, violent window. One leading idea involves hypothetical super-heavy particles predicted by grand unified theories, which decayed ever so slightly more often into matter than antimatter as the universe cooled. Another possibility lies in the behavior of neutrinos, those ghostly particles that barely interact with matter. If neutrinos are their own antiparticles, a special type known as Majorana particles, they could have triggered processes that favored matter creation. Some theories even tie the matter asymmetry directly to the dynamics of cosmic inflation, suggesting the same field that drove the universe's exponential growth also planted the seed for our material existence. Without a solution to this problem, our entire cosmic story is incomplete. We can trace the expansion from a hot, dense beginning to a cold, vast present, but we cannot explain why there is anything here to expand at all. The existence of galaxies, stars, and conscious observers hinges on a 1 in a billion fluke written into the laws of physics during the first fractions of a second. It is the ultimate reminder that we are not just living in the universe. We are the improbable, precious remnant of a broken symmetry. That 1 in a billion fluke gave us a universe of matter, but it did not distribute that matter evenly. On the grandest scales, we are all caught in a cosmic river, flowing toward a mysterious destination. This brings us to the nature of the Great Attractor, a gravitational anomaly so powerful it bends the paths of entire galaxies. For decades, astronomers have mapped the motions of galaxies, not just the smooth expansion driven by dark energy, but their individual, peculiar velocities, the drift and flow superimposed on the cosmic current. And they found something astonishing. Our entire local group of galaxies, along with thousands of others across a region hundreds of millions of light years wide, are all being pulled in the same direction, toward a point in the sky near the constellations Centaurus and Hydra. We are moving toward this unseen focal point at a staggering speed of over 1 million miles per hour. Something with the mass of tens of thousands of Milky Ways is reeling us in. This is the Great Attractor, a gravitational heart of darkness hidden behind the thick dust and stars of our own galaxy's plane, an area astronomers call the zone of avoidance. For a long time, it was a ghost, a pull without a source. But modern surveys that can peer through the galactic murk with X-ray and radio eyes have begun to reveal its face. The Great Attractor is not a single, monstrous object. It appears to be the core of the Laniakea supercluster, an immense filament of galaxies spanning 500 million light-years. At its center lies the Norma cluster, a dense knot of galaxies and hot gas with a truly enormous collective mass. This supercluster complex is the gravitational anchor for our entire galactic neighborhood. Yet, even this colossal structure seems insufficient to fully explain the observed motion. The pull is so strong that it suggests there is even more mass behind the Great Attractor, something even larger tugging on it, and us in turn. This hints at an even grander flow, a vast river within the expanding universe where superclusters themselves are in motion, pulled by the gravitational influence of unimaginably large overdensities of matter, regions where the cosmic web is thickest. The great attractor, then, is a waypoint, not the final destination. It is a signpost pointing to structures so immense they shape the motion of galaxies across billions of light years. A reminder that while dark energy pushes space apart on the largest scales, the gravitational memory of where matter clumped first still writes the trajectories of everything within it. We are surfing a wave set in motion when the universe was young, a testament to the fact that the cosmos is not just expanding, it is also profoundly in motion. These immense cosmic currents are charted by the faintest whispers, signals that cross billions of light years in a blinding flash. Fast radio bursts are among the most mysterious events in the modern universe. Lasting only a few thousandths of a second, they unleash more energy than our sun does in 80 years, all packed into a single, brilliant pulse of radio waves. They arrive without warning from random points in the sky, often from galaxies so distant their light has traveled for billions of years to reach us. For over a decade after their discovery, they were complete enigmas, cosmic one-hit wonders that appeared and vanished in an instant, leaving astronomers scrambling for an explanation. What kind of celestial catastrophe could possibly produce such a brief, yet unimaginably powerful, signal? The suspects read like a roster of the universe's most extreme objects. A neutron star, the crushed core of a dead sun, with a magnetic field trillions of times stronger than Earth's, could suddenly crack and release a quake of energy. A supermassive black hole violently shredding a passing star could generate a final scream of radio waves. Some theorists have even proposed the collisions of exotic objects, like two neutron stars spiraling together in a final, fatal embrace. The mystery deepened when astronomers found something astonishing: repeating fast radio bursts. Unlike the one-off events, these sources would fire off multiple bursts, sometimes in a frantic, unpredictable pattern. This ruled out any purely cataclysmic, destroy-the-source event for those repeaters. It pointed instead to an engine that could survive its own outbursts, something like a highly magnetized, spinning neutron star known as a magnetar. In fact, a magnetar in our own galaxy was observed producing a fast radio burst-like signal, providing a crucial clue, but the story is far from solved. Many bursts, especially the non-repeaters, may still come from different, more destructive sources. We are likely hearing a chorus of different cosmic instruments, all playing the same shocking note. Yet, these mysterious signals are more than just cosmic fireworks. They are becoming one of our most powerful tools for mapping the invisible universe. As a fast radio burst travels across the vast intergalactic voids, its journey is not through empty space. It passes through the diffuse gas of the cosmic web, the thin plasma of protons and electrons that stretches between galaxies. This material slows down the lower frequency parts of the radio signal ever so slightly more than the higher frequencies. By the time the burst reaches us, it is stretched out or dispersed, like a chord played on a piano that arrives as a slow, descending glissando. The amount of this dispersion is a direct measure of how much stuff the signal has traveled through. Each fast radio burst is, in effect, a cosmic dipstick. By measuring its dispersion from a known distance, astronomers can tally up all the ordinary matter, the atoms and ions, that it encountered along its path. This provides a crucial, independent census of the universe's normal matter, the 5% that makes up stars, planets, and us. For decades, our estimates of this normal matter have come from adding up all the glowing objects we can see and the hot gas we can detect. but a significant amount was thought to be missing, hiding in the warm, diffuse filaments of the cosmic web. Fast radio bursts are now confirming that this missing matter is indeed there, woven through the vast voids. This matters profoundly for our models of cosmic expansion. The amount and distribution of normal matter, along with dark matter, set the gravitational landscape that either resists or aids the push of dark energy. By using these fleeting radio flashes to independently verify the cosmic matter budget, we are performing a critical cross-check on the entire expansion history of the universe. A mysterious millisecond signal from a distant galaxy thus becomes a precise tool, a fleeting beacon that illuminates the shadowy scaffolding of everything. That faint, universal background hum does more than just map temperature, it defines a direction. This leads us to a question that strikes at the very heart of Einstein's relativity. Is there a preferred frame of reference? The theory of relativity is built on a beautiful democratic principle. The laws of physics are the same for all observers, no matter how fast or in what direction they are moving. There is no special, absolute state of rest against which all motion can be measured. Your frame of reference is just as valid as anyone else's. Yet, the cosmic microwave background presents us with a profound complication. When we measure its temperature, we find that dipole, that hot and cold pole. As we discussed, the standard interpretation is that it is caused by our own motion. But to say we are moving, we must be moving relative to something. That something is the cosmic microwave background itself. It provides a universal, all-sky reference frame. In the frame where this ancient light is perfectly isotropic, perfectly the same in every direction, you would be at absolute rest with respect to the expansion of the universe itself. This is often called the CMB rest frame. From this perspective, every galaxy's motion can be split into two parts: the smooth Hubble flow, the expansion of space carrying it outward, and its own peculiar velocity, its drift within that flow. The CMB gives us a cosmic ledger to measure that drift. This creates a fascinating philosophical and physical tension. Does the existence of this rest frame violate the spirit of relativity? Not technically, because relativity deals with the laws of physics in inertial frames, and the CMB frame is not special in that regard. The laws still work everywhere, but it is uniquely special in a cosmological sense. It is the frame in which the universe appears most uniform, the frame defined by the very fabric of space-time as it has expanded since the beginning. In a very real way, it defines the center of our observable universe, not a point in space, but a state of motion. We are not at the center. Every observer anywhere in the cosmos would see their own CMB dipole, their own motion relative to this universal backdrop. Each would have their own center. This is a crucial distinction. The CMB rest frame does not pick out a location, but it does pick out a velocity. It tells us we are moving at about 600 kilometers per second relative to the grandest stage of all. This has led some physicists to ask a radical question. Could this preferred cosmological frame be more than just a convenient reference? Could it be baked into the laws of gravity themselves? Theories of modified gravity, like MEND, which seeks to explain galaxy rotations without dark matter, sometimes incorporate such a frame. More extreme ideas suggest the possibility of Lorentz violation, meaning the fundamental symmetry of relativity could be very slightly broken on cosmic scales, with the CMB frame acting as the breaker. If true, the implications would be staggering. It would mean that absolute motion, the very idea Einstein sought to banish, has a subtle meaning in our expanding universe. It would redefine what we mean by the expansion itself. Is space stretching, or are we all simply moving apart within a fixed, absolute framework? For now, the CMB frame stands as a cosmic gift and a profound puzzle. It is the ultimate calibration tool, allowing us to subtract our own motion and see the universe as it truly is, expanding uniformly in all directions. Yet its mere existence whispers that in the vast theater of the cosmos, there might just be a special seat, a state of perfect rest, from which the entire symphony of expansion is meant to be heard. That universal backdrop of motion frames the growth of the most voracious objects in existence. At the centers of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole. These are not merely dead stars. They are cosmic monsters with masses millions to billions of times that of our Sun. And their origin story is one of the most pressing puzzles in modern cosmology. The deepest mystery is not just that they exist, but when they appeared. Our most powerful telescopes have spotted quasars, the blindingly bright beacons powered by supermassive black holes greedily feeding on gas shining from the universe's infancy. We see them blazing away when the cosmos was less than 1 billion years old. This presents a staggering timing problem. How did a black hole grow to a mass of 1 billion suns in what is, cosmically speaking, the blink of an eye? For a black hole to grow, it must feed. It pulls in gas and stars, but even under ideal conditions, there is a speed limit called the Eddington limit. This is the point where the radiation blasting out from the infalling material pushes back so hard it chokes off the flow. To reach such colossal masses so quickly, these first black holes would have had to feed at or above this theoretical maximum for their entire brief lives. It is like trying to explain how a newborn baby grew to the size of a blue whale in just a few months by eating non-stop. The math is brutally difficult. So scientists are forced to consider more exotic beginnings. One compelling idea is direct collapse. In this scenario, the very first massive clouds of primordial gas in the early universe did not fragment into many small stars. Instead, they collapsed directly in one catastrophic fall, into a single monstrous black hole seed with a mass tens of thousands of times that of the Sun. This gives the black hole a huge head start, a massive seed from which it can then grow more reasonably into the behemoths we see as quasars. But this process requires very specific conditions, a cloud that is metal-free and can cool slowly enough to avoid breaking apart. It is a delicate cosmic recipe that may have been rare. An even more radical possibility connects these giants to the universe's very first moments. Could supermassive black holes be the grown-up versions of primordial black holes, formed not from dying stars, but from the extreme density fluctuations in the first second after the Big Bang? In the chaotic frenzy of the early universe, pockets of space could have become so densely packed that they directly pinched off into black holes of all sizes. Some of these primordial seeds, born with substantial mass, could have sunk to the centers of the first protogalaxies and begun their feast immediately. This idea elegantly solves the timing problem, but it creates others. We have not found conclusive evidence for these primordial black holes, and their existence would have left subtle imprints on the cosmic microwave background and the distribution of matter that we have yet to detect. The growth of these black holes is inextricably linked to the expansion history of the cosmos itself. In the early universe, space was smaller and denser. Matter was packed more tightly together, and galaxies were closer, merging more frequently. Each galactic collision would funnel fresh gas toward the central black hole, fueling incredible growth spurts. The expansion rate at that time set the clock for how quickly structures could form and merge. A slower early expansion, as hinted at by some models, would have allowed matter to clump together faster, providing a richer banquet for these growing monsters. Conversely, a faster expansion would have spread the cosmic buffet more thinly, making their rapid growth even harder to explain. The supermassive black holes we see today are not just relics, they are active participants in the cosmic story. Their fierce radiation and powerful jets can heat surrounding gas, preventing it from cooling to form new stars, effectively regulating the growth of their host galaxies. This intricate feedback loop connects the smallest scales of gravity's ultimate victory to the largest scales of galactic evolution. Solving the mystery of their origin is more than an exercise in accounting for cosmic monsters. It is a direct probe into the conditions of the early, expanding universe, a test to see if our timeline of cosmic structure can accommodate such impossibly bright beacons shining from the dawn of time. These cosmic monsters present a paradox that threatens the very laws of physics. What is the fate of information in black holes? At first glance, this seems like a question for quantum physicists, a puzzle about the smallest scales. But its resolution is deeply entangled with the ultimate fate of the entire cosmos, linking the death of stars to the birth of the universe. The problem begins with a shocking prediction by Stephen Hawking. He realized that black holes are not completely black. Due to strange quantum effects at the very edge of their gravitational grip, the event horizon, they should slowly evaporate, emitting a faint glow of particles now called Hawking radiation. This radiation is purely thermal, like the heat from a stove. It carries no specific information about what fell in. A black hole formed from a collapsed star and one formed from a collection of old books would, according to Hawking's original math, emit identical radiation as they evaporated. And here lies the paradox. In quantum mechanics, information is sacred. The state of every particle in the universe is encoded in a wave function, and that wave function evolves in a predictable, reversible way. Information cannot be destroyed. You can burn a book, but in principle, if you could collect every ash particle and photon of light, you could reconstruct every word. But if a black hole evaporates completely, leaving behind only this generic thermal radiation, then the information about everything that ever fell into it, the star, the books, the history of entire planets, is lost forever. It vanishes from our universe, violating a cornerstone of physics. This is the black hole information paradox, a crisis that has divided theoretical physics for decades. Does information truly get destroyed, forcing us to rewrite quantum theory? Or is it somehow preserved, scrambled and encoded into the Hawking radiation in a way we do not yet understand? The leading idea for a solution comes from the holographic principle, a concept that feels like it is from science fiction. It suggests that all the information contained within a volume of space, like the interior of a black hole, can be completely described by data encoded on its boundary, its event horizon. Think of it like a three-dimensional movie being projected from a two-dimensional screen. The information about everything inside the black hole is not lost, but smeared and stored on its surface, and then slowly leaked back out in the radiation. This is not just a clever trick for black holes. The holographic principle hints at a radical nature of reality itself, suggesting that our three-dimensional universe might be a projection from a two-dimensional surface at the cosmic horizon. This is where cosmology crashes into the paradox. To truly solve it, we need a complete theory of quantum gravity, a framework that unifies Einstein's theory of gravity with quantum mechanics. Such a theory does not yet exist, but we desperately need it, not just for black holes, but for the very beginning of time. The Big Bang started from a singularity, a point of infinite density where our laws of physics break down. To understand what happened at time zero, to know if there was a before, or if our universe emerged from something else, we require that same theory of quantum gravity. The information paradox and the origin of the universe are two sides of the same coin. Both involve a singularity where gravity becomes quantum. Solving how information escapes a black hole may provide the mathematical tools to understand how our entire cosmos escaped from its own primordial singularity. The fate of every bit of information that falls into a black hole is a microscopic rehearsal for the ultimate question of what happened to all the information, the initial conditions of the Big Bang itself. In seeking to understand how things end in the darkest places, we might finally learn how everything began. The quest to understand our cosmic origins leads us to hunt for ghosts in the fabric of reality itself, relics that could be woven through the void. Can we detect cosmic strings? These are not strings in any ordinary sense, but hypothetical cracks in the universe, unimaginably thin defects in spacetime that may have formed in the first split second after the Big Bang. To picture one, think of the universe cooling from a state of perfect, symmetric chaos, like water freezing into ice. When ice forms, the crystalline structure doesn't always align perfectly. Defects and cracks appear where different regions of order meet. Cosmologists believe something similar happened as the newborn cosmos cooled and underwent profound phase transitions. The fundamental forces we know today, gravity, electromagnetism, the strong and weak nuclear forces may have been unified as one superforce. As the universe expanded and cooled, this symmetry broke and the forces split apart. In that violent breaking, flaws might have been trapped in the fabric of spacetime, cosmic cracks of concentrated energy. A cosmic string would be a one-dimensional crack, a line of pure mass energy thinner than a proton, but stretching across the entire observable universe. Its density is almost beyond comprehension. A single inch of this string could weigh as much as a mountain range. These filaments would be under immense tension, whipping through space at nearly the speed of light, and their gravitational influence would be profound. So how could we possibly find such an exotic thread? Astronomers have two primary hunting strategies. The first looks for their effect on light. The immense mass of a cosmic string would warp spacetime around it, acting as a gravitational lens. But unlike a galaxy or a black hole, a string's lensing signature would be unique. It would not create distorted arcs or Einstein rings. Instead, it would produce a perfect double image of any galaxy or quasar, lying directly behind it, with no distortion at all. It would be like looking at a crack in a window pane and seeing a streetlight perfectly duplicated on either side. Surveying the sky for such perfectly matched pairs of distant objects is an ongoing needle-in-a-haystack search. The second strategy looks for their imprint on the oldest light we have. As a cosmic string whips through the primordial plasma of the early universe, it would create ripples. These disturbances would leave a specific, sharp signature in the polarization patterns of the cosmic microwave background, a distinctive swirl or B-mode pattern that other processes, like inflation, might also create but in a different form. Isolating that specific fingerprint is a monumental challenge, but next-generation observatories are designed to look for it. Discovering even one cosmic string would be a revolution. It would be a direct fossil from the universe's first moments, a snapshot of physics at energies a trillion times greater than anything our particle colliders can reach. It would provide tangible evidence for the grand unified theories that attempt to describe how the forces of nature split apart. More than that, the properties of a cosmic string, its tension, how it moves, would tell us about the exact nature of that primordial phase transition. It would reveal the specific way symmetry broke in the infant cosmos, which in turn dictated how matter clumped, how forces separated, and set the initial conditions for the expansion we see today. These hypothetical cracks are more than cosmic curiosities. They are potential signposts from the very instant the rulebook of our universe was written, threads left behind from the moment the cosmic tapestry began to weave itself. Finding one would mean we could finally read a sentence from that first, lost chapter of everything. These cosmic cracks and threads are woven into a tapestry of breathtaking scale, a tapestry defined as much by its emptiness as by its splendor. Between the great luminous filaments of the cosmic web lie the true titans of space, the voids. These are not simple gaps, but vast, expanding bubbles of near-nothingness, regions hundreds of millions of light years across where galaxies are scarce, and the density of matter is a tiny fraction of the cosmic average. They are the dominant feature of our universe by volume, the great negative spaces in the sculpture of creation, and their behavior may hold a key to one of our deepest modern mysteries. Consider our own cosmic address. We do not reside in the dense heart of a supercluster, but in a more modest suburb. Recent mapping suggests our local group of galaxies sits within a staggeringly large void, now known as the Kibisi Void, named for the astronomers who identified it. This void is a spherical region roughly 2 billion light-years wide, where the density of galaxies is about 20% lower than the surrounding universe. We are living in a local underdensity, a cosmic countryside. This fact is not just a curiosity, it is a potential game-changer for how we measure the cosmos. Because gravity works both ways. While matter pulls matter together, creating dense clusters, the absence of matter has an opposite effect. Inside a giant void, the gravitational pull from the surrounding walls of the cosmic web is asymmetrical. There is less mass inside to hold things back. This creates a subtle but real effect. Voids expand slightly faster than the universe's global average. Space inside them stretches a little more quickly. Now, think back to the Hubble tension, that stubborn disagreement between the early universe and local measurements of the expansion rate. Our local measurements, using supernova and Cepheid stars, are all made from inside this Kibisi void, from our position in a region of below average density. What if we are, quite literally, living in a cosmic bubble that is inflating faster than the rest of the universe? Our telescopes would faithfully measure that faster local expansion and report it as the Hubble constant, while the cosmic microwave background, which averages over the entire sky and thus the entire universe, would give us the slower, true global average. The void phenomenon offers a tantalizing, elegant solution. It suggests that the expansion of the universe is not perfectly uniform on the scale of a few billion light-years. Instead, it has a texture, a topography. The Hubble constant might not be a single, universal number, but a local variable that depends on where you measure it from. We may have been like sailors trying to measure the average depth of the ocean, but doing so only from inside a deep, fast-draining whirlpool. This idea is being tested right now. Cosmologists are creating sophisticated maps of the cosmic web in 3 dimensions, using galaxy surveys to pinpoint the size and density of voids with incredible precision. They are then measuring the expansion rate in and around these voids, looking for that predicted speed up. Early results are intriguing, suggesting that yes, voids do expand faster, and the effect could be large enough to account for a significant portion of the Hubble tension. But the implications run even deeper. If voids expand faster, they are actively shaping the future of the cosmos. As they grow, they become ever more empty, their internal pressure dropping. The surrounding walls and filaments of the cosmic web, under the relentless pull of their own gravity, will eventually thin and stretch, feeding more matter into the clusters at their intersections. The voids are the engines of cosmic isolation, destined to become the true, dominant feature of the far future universe, as dark energy pushes their boundaries ever outward. Our local void, then, is not just our home. It is a laboratory, a unique vantage point from which we are measuring a universe that is not smooth, but frothy, a place where the rate of expansion itself whispers the story of the great, growing emptiness all around us. The great, growing emptiness of cosmic voids is a feature of the universe in time. But what if time itself is not what it seems? This brings us to the final, most profound question of all, a mystery that lies at the very edge of physics and philosophy. Is time an illusion? Our entire experience of reality is built on the relentless flow of time, from the ticking of a clock to the aging of stars. Yet, when we push our theories to their absolute limits, time begins to dissolve. In Einstein's theory of relativity, time is woven together with space into a single four-dimensional fabric called spacetime. But crucially, relativity treats time as just another dimension, like length, width, and height. In this view, the universe is not a movie that plays out frame by frame. It is more like a finished sculpture, a block universe where the past, present, and future all exist simultaneously, laid out in the unchanging marble of spacetime. Your birth, this very moment, and your last breath are all equally real, just at different coordinates. The feeling of flowing from one moment to the next, the sensation of a moving present, is, in this picture, a kind of persistent trick of our consciousness. We are like readers moving through a book, experiencing the story one page at a time, even though all the pages already exist, fixed and complete. This block universe is a direct consequence of relativity and is consistent with all our observations. But then we turn to the other pillar of modern physics, quantum mechanics, and the quest to unify it with gravity. Here, the problem of time becomes even sharper. In some of the most promising approaches to quantum gravity, like the Wheeler-DeWitt equation, time vanishes completely from the fundamental description of the universe. The equation describes a static, timeless reality. It is as if the most basic laws of physics make no mention of clocks or change at all. This is the deep puzzle. How does our vivid, flowing experience of time emerge from a timeless foundation? One compelling idea is that time is not fundamental, but emergent, a collective property that arises from the relationships between things, much like temperature emerges from the frantic motion of atoms. In an expanding universe, this emergence may be tied directly to the growth of entropy, the measure of disorder. The Big Bang represents a state of incredibly low entropy, a highly ordered starting point. From that unique beginning, the universe has been evolving toward higher entropy, and this irreversible march gives us a powerful arrow of time. We remember the past, not the future, because the past is a state of lower entropy. The expansion of space itself may be the engine driving this increase, creating more room for disorder to grow, and in doing so, generating the very flow of time we perceive. So what does this mean for the beginning and the possible end? If time is emergent, then asking what happened before the Big Bang might be as meaningless as asking what is north of the North Pole. The Big Bang may not be an event in time, but the moment time itself began to emerge. Conversely, in a universe that expands forever into a cold, empty void, a state known as heat death, entropy will eventually reach its maximum. Change will cease. With no processes to distinguish one moment from the next, the arrow of time may effectively vanish. The universe would become static and timeless in practice, even if not in its fundamental equations. The endless expansion could lead to the gradual fading of time itself, so we are left with a breathtaking inversion. We live our lives immersed in the river of time, planning for the future, remembering the past. Yet our best scientific descriptions suggest this river may be a shimmering mirage on a timeless shore. The expansion of the universe, from its explosive birth to its dark energy-driven fate, may be the very process that conjures this illusion into being, giving us a story to live within. The final unsolved question is not just about the cosmos out there, but about the nature of our own consciousness, reading the eternal pages of a book that writes itself as it expands. These 25 questions are not isolated riddles, but interconnected strands in a single grand tapestry. The mystery of dark energy is woven into the fate of the universe. The hunt for dark matter shapes the growth of galaxies. The whispers of the cosmic microwave background echo the violence of inflation, and the ghost of the lithium problem haunts the first nuclear forge. Each thread pulls on another, revealing a cosmos far more complex, dynamic, and strange than we ever imagined just a century ago. To stand before this tapestry is to feel a profound sense of humility. We have mapped the universe from its first 3 minutes to its accelerating fate. Yet we must admit that most of it is made of substances we cannot see, governed by forces we do not fully understand. The foundational laws themselves, from the constancy of physics to the nature of time, are now open questions. This is not a failure of science, but its greatest triumph. We have progressed far enough to finally see the true depth of our ignorance, and that is a thrilling place to be. We are living in a golden age of cosmic discovery. The James Webb Space Telescope is peering into the dawn of the first galaxies. The Vera C. Rubin Observatory will soon begin a decade-long movie of the night sky, watching for subtle changes that reveal dark energy's secrets. New gravitational wave observatories will listen for the echoes of black hole collisions and perhaps the faint hum from the Big Bang itself. These tools are not just answering old questions, they are uncovering mysteries we have not yet even dreamed of. So stay curious. Follow these discoveries as they unfold. Look up at the night sky and remember that every point of light is part of a story still being written, a story of expansion, mystery, and profound beauty. And we want to hear from you. What cosmic mystery captivates you the most? Is it the haunting possibility of a multiverse, the unsettling crack of the Hubble tension, or the silent pull of the Great Attractor? Share your thoughts in the comments below. If you want to join us as we explore these frontiers, be sure to subscribe. Our journey through the universe's greatest secrets is just beginning.